Today we start Module 1 Part B, Role of Data Structures and Optimality of Algorithms. Part B.1, Horner's Rule. Last time we tried to find an efficient way to evaluate polynomials. We were halfway there. We didn't complete it because we ran out of time. So now let's continue. So we complete the remaining part. All right. So now, we work on the same problem, but this time we continue the part we left last time. So first I want to recall a little bit. So I hope you still remember the point where we are. All right. We just finished process polynomial of degree 2, quadratic polynomial. Yeah. We can call it quadratic polynomial, degree 2. The technique we found, a very smart technique we found based on the property of common factor. So we use the factorization technique. After the factorization, we reduce the number of multiplications. So that's where we were last time. Here you can see the key of success is factorization. Why? We can improve the performance by reducing the number of multiplications because we catch that critical property and take advantage of it. Then we use this factorization technique to get a good result. All right. From this, summarization, let's push one step further to complete the whole problem. All right. Strategy for generalization. Now we want to generalize this idea to the general case. So we need to have a strategy. So for this class, you can see I always talk about strategies. We really need effective strategies. Here, another one. All right, so what kind of strategy we need? This is strategy. Do factorization as much as we can. We know in this problem, the factorization technique helps us a lot. Why? So it is very natural we should apply factorization as much as we can. So here I emphasize this part, as much as we can. Okay? But the question is, how do you implement this idea, as much as we can? Right? So the second, after we get the direction, the next, implementation. How do we make it happen as much as we can? All right. So here, let me point out another interesting idea. Greedy idea. Greedy algorithm. Greedy. So greedy, people don't like to be called greedy, right? Usually. But here in our algorithms, the name we use here, it's not a bad thing. Yeah. It helps us a lot. Yeah. Actually, here, another thing I want to let you know, we are doing module 1 here. When we reach the end of semester, when we work on module 8, we will learn the greedy algorithms. But in this early, we need to use the greedy idea. So that's already sort of the content we will learn in module 8. Yeah. Anyway, because here it is very important. So we want to apply that interesting idea. Very simple, very easy, very effective. So let's just do it. The greedy idea is, based on your intuition, try to be greedy. When you make your decision, try to be as greedy as possible. Look at here. As much as possible, as greedy as possible, similar, right? So you try, because the greedy original meaning, try to get money as much as you can, right? That's greedy. But here we try to get the best performance as much as we can. Okay? So that kind of analogy here. All right. How to do that? Here, more specifically, we try to use the factorization as much as you can, as we can. Yeah, we try to use factorization, the key part of our technique, as much as we can. That's the greedy meaning here. That's the, specific greedy meaning in this question. Yeah. All right, next we will do it. All right, let's do our work here. When we do our work, I want to use another specific example when n equals 3. So here we have when n equals 3, we have a cubic polynomial. Yeah. From quadratic polynomial to a cubic polynomial. Yeah. And here we try to be greedy when we use the factorization technique. The factorization should cover, what do you mean to be greedy using factorization? The specific meaning is the factorization should cover as many terms as possible. Okay, so here you can see as many something as possible, as much as possible. This kind of thing, this phrase kind of related to greedy action, right? Yeah, so let's do it. Try to be, when we do factorization, we try to cover as many terms as possible. Right? So let's do it. Here, you can see, definitely our factorization cannot cover all 4 terms, right? Because these 4 terms do not have any common factor. So it cannot cover all the terms. So let's reduce 1. Can we cover 3 terms? Yes, we can, because the last 3 terms, they share a common factor. So we can factor that x out. Okay? So then we have some remaining terms inside the parentheses. Yeah. That's the first time we apply the greedy strategy. This is greedy strategy to apply it. All right. Then, for the remaining terms, do the same factorization. Yep. Because we have this weapon. It's a nice weapon. Let's apply it again and again. Okay? Yeah. To be very greedy, right? To be very, very greedy. All right. So when we apply next time, because the remaining term inside the parenthesis, we can apply this factorization another time, try to cover as many terms as possible, but we leave out the first term, so that cover the remaining 2 terms. In that way, we get another round of factorization. See? Can we generalize this idea to the general case? Yeah. Next, we push this method to the general case. That should be quite straightforward. After we go through all these steps, it should be quite straightforward. All right. Now, finally, for the general case, the factorization, level by level, step by step, round by round, we get this expression. Okay? After you get this expression, this is the famous Horner's rule. The famous Horner's rule. Horner, so this guy discovered it hundreds of years ago. Okay, long time, hundreds of years ago. That old, but very, very smart. Okay, very, very smart. After we get this one, now let's look at how many multiplications do we need. How many multiplications? All right, here we need to do the counting. We still use the technique we used the last time. Counting by reference. Counting by reference. We used several times before. All right, now another time. Can you try a little bit by yourself? Can you tell me? No, here I cannot hear. You can try. How many multiplications can you find from this expression? Okay, here, let me do it. This is the first multiplication. I want to associate this multiplication to some fixed reference number. Here, I associate this multiplication to the subscript A1. 1, okay? A1. That 1 is my reference. All right. Then the second multiplication, I associate with second subscript A2. That 2. Okay? And so on. Then this multiplication associated to n-1. The last multiplication associated to n. Now, is this one-to-one correspondence? From object 1, math object 1 multiplications to math object 2 subscripts, right? Subscripts of coefficients. Object 1, object 2, one-to-one correspondence. Object 1, not that easy to count, but object 2, very easy to count, right? How many elements in object 2? So we count the number of multiplications and, right? Because we count 1, 2, 3, all the way through n. Obviously, n elements, right? So our answer is n. All right. So now, conclusion. After we get that, conclusion. Multiplication reduction. So this time, we want to look at the multiplication reduction. Before we do the reduction, this is our expression. 1/2 times n minus 1. It is a quadratic formula. Okay? After reduction, just n. Just n. Is that big? Think by yourself. Is that a big reduction? Big improvement? Right? How much is the difference? Can you feel it? Although I think most of us will agree this is a big improvement. But it is very hard to feel about how large is the improvement. Can you feel about it? Can you get a concrete, concrete visualization of this difference? It's not easy, right? It's not easy. All right. We will do that. In order to see that concrete visualization, we may like to do it. So let's look at the impact of the multiplication reduction. For this particular problem, we have two different algorithms. The improvement, how big is the improvement? How big is the impact of the improvement? So let's look at that question in this slide. All right. The formula reduction is like this, but how to feel about it? So that's what I mean. it's very hard to feel about how big is the difference. So we need to do it. We need to do the visualization on it, right? Yeah, to get a huge impression. Okay, yeah. All right. Let's work on some examples to see the big difference. Concrete examples to see big difference. Here, I just want to use two examples, two simple examples. Then that should be enough to see the big difference. The first one, when n equals 1,000, you plug in those two formulas so you can see the difference clearly. The first one, n 1,000, then you plug in the second formula. Here, I omit that plus 1. The reason is the approximation, the difference is not that big, but I can get a relatively easier number to compare, right? For convenience. Yeah. The difference I make very small, so I like to use the approximation here. All right, so we get 500,000 from the left-hand side, 1,000 at the right-hand side. What is the ratio? 500 to 1. Is that big? 500 to 1 ratio. So you improve your algorithm by 1 to 500. In other words, when you use the older method, you need a certain amount of time, but after you switch to the new method, you only need 500th time. 500th time. Is that big? Is that big? Yeah. As I mentioned before, even you get 1/10 improvement. That's pretty significant, right? But this time, 500th improvement. That's really something. Big thing, right? All right. Our example number 2. When n equals 1 million, how about it? N equals 1 million. It looks a large number, but right now, in our big data era, now, people always talk about big data. Do you think 1 million data items should be considered a reasonable data size? Yes, right? Yeah, reasonable data size, 1 million, just 1 million, not 1 billion, right? We can easily get to 1 billion, right? So here I only take 1 million. So to not scare you, yeah, 1 million here. All right. Let's plug in those two formulas and compare the difference. Right-hand side, 1 million. Left-hand side, how big is it? I still use the approximation. Skip that 1, but this number, I think you can tell me, right? How big is this number? 500 billion. 500 billion. Let's take the ratio. 500,000. Yeah. Sometimes, I cannot quickly get the right expression. 500,000 to 1 ratio. 500,000 to 1 ratio. Is that big? Is that huge? Right? Yeah. How do we feel about the big difference? Here, I ask you another time, because we want to visualize it. We want to really get something using our familiar experience to feel about it. That's something missing here. So the last thing I want to do in this video, feel about it. Okay. What should I do? I add time unit, because here there is no time unit, right? I intentionally add time unit to it. S, second. Okay? I add second, both sides. Okay? The right hand side, 1 second. The left-hand side, 500,000 seconds. Let's compare that difference. Right-hand side, suppose you can solve the problem using 1 second. That's pretty fast. All right. But left-hand side, if you use the older algorithm, you need 500,000 seconds. But you may not have a concept. How large is this number, right? You know it's big, but how big it is, you may not get any idea. So let me do the conversion. I convert this many seconds to the number of days. Then you have an idea. Approximately 5.8 days. Less than 6 days, 5.8 days. You have an idea how long is 5.8 days, right? Yeah, almost 1 week, close to 1 week, right? Yeah. So now you get an idea. The visualization is 5.8 days versus 1 second. How big is the difference? Okay? Yeah. To summarize it, there are two algorithms. One smart, one very slow. Okay? You use both algorithms to solve the same problem. The smart one, you only need 1 second. The poor one, yeah, that's called the poor one, you need 5.8 days to do the same thing. Now, tell me the impact of the efficient algorithms. You can see the conclusion is the impact of efficient algorithms is huge. Okay, all right, so that's part B.1.